What if the laws of physics aren't really written in the language of geometry, but in the language of probability? What if the very fabric of space-time is just a shadow cast by data? You first have to see how physicists and statisticians kind of look at the world from two different angles. You've got the physics of what is, and then you have the information theory of what could be. Theoretical physics gives us the stage where everything in the universe happens. That's space-time, with all its particles and forces. Information geometry, on the other hand, well, it creates a map of possibilities. It's not describing a physical place, but instead it measures the distance between different predictions. What if that map is the stage? The Fisher-Rao metric. You just start with two statistical models that are really similar. Then you figure out how easily you could tell which curve the data came from. And finally, you turn that distinguishability into a number, a precise geometric distance. What happens when we use it to measure the shapes of the most basic statistical ideas we have? Let's start with the simplest possible thing, a single coin toss, right? The only thing you need to know is the probability P of getting heads. In stats, they call this a Bernoulli distribution. So what shape does the space of every possible coin make? A perfectly straight, flat line. It has zero curvature. Let's look at something we all know, the bell curve, or the Gaussian distribution. The space of all possible bell curves is not flat, not even close. It has the shape of a hyperbolic saddle with a constant negative curvature. How about a simple three-way choice? This is basically just a model for picking between three different things. Think rock, paper, scissors. And the geometry of that? It's a piece of a sphere. This geometry is basically telling us that the probabilities are all connected. The pattern is just undeniable. The simplest, most fundamental tools in statistics don't just create random, messy shapes. They naturally give us the three most fundamental geometries that exist: flat, spherical, and hyperbolic. Why does any of this actually matter? This quote from the paper just nails it. The geometry is no longer an assumption, it's a result. And that is so important because of a core rule in all of physics. Geometry tells things how to move. The shape of the stage defines the rules of the game. Geometry isn't just a passive background, it's an active participant. What does all this mean? It means the very shape of our universe might not be the most fundamental thing. It could actually emerge from the rules of information. It means we have this incredible new bridge connecting the worlds of statistics and physics. And this could let us build physical theories by looking at the shape of data. And it's not just for physics. This is a whole new way to think about complex systems in biology, in AI, everywhere.